Hello everyone, this is Dr. Young, and we are going to talk about the Wittig reaction, which is one of my favorite reactions because I'm going to say 100 of them probably in grad school. I use this reaction a ton. So let's talk about what it is, why is it useful, and we'll look at some examples. So the Wittig reaction, this is just a reaction between aldehydes and ketones, a little faster with aldehydes obviously than ketones, and it reacts with a phosphorus ylide, which is a new term for us. You might remember hearing about ylides when you looked at the Swern oxidation that had a sulfur ylide as part of the mechanism. This is a phosphorus ylide, and the term ylide just refers to when you have two atoms, and I'll just label these atoms as like squares because it doesn't really matter if they're oxygen, carbon, whatever. But one of them is positive and one of them is negative, and they're right next to one another. That's what an ylide is. So for these reactions, we're going to see a lot of phosphorus ylides, which just means that one of those two atoms is a phosphorus. So like a classic example of a Wittig reagent would be a phosphorus attached to a carbon. Let's just say this is a CH and then whatever. And this carbon is going to be negative. It's going to have its lone pair and it's going to be negative. And this phosphorus is going to be positive. And the phosphorus will be attached to three more things to make it positive. It's right below nitrogen, remember, so when it has four groups, it's a formal charge of +1. What you're almost always going to see from me and in most books and most reagents that you buy online is that the three groups that are on the phosphorus are phenyl rings. So it's almost always this triphenyl phosphorus ylide. Technically, you can make ylides with things that aren't triphenyl phosphorus based, phosphine based, but you're probably not going to see them. So the thing with the ylides is phosphorus can have an expanded octet, right? And so this lone pair from the negative on the carbon can actually drop down, and you can draw a resonance. It's like a resonance structure, right? Where if you look at this resonance structure, now I've got a phosphorus with the three phenols. Now it's double bonded to the carbon that has the H and the R group. So you've got this resonance stabilized charge thing. One has charge separation, one doesn't. And so you'll see ylides drawn in one of these two forms, sort of willy-nilly. You tend to draw the one with the double bond more often than separate, but I'll show both because it really helps with like the mechanism and thinking about where things go. But so an ylide is when you have opposite charges on adjacent atoms that can split and kind of recombine like this. And in our case, all the Wittigs come with phosphorus ylides. So, like for example, down here in this one, right, I have this sort of like isobutyl ylide, and I could redraw this. I'll just go ahead and redraw the resonance structure just so you can see it to kind of emphasize what we just talked about. Right, here's the ylide drawn in the double bond form, and I'm just going to redraw it out here so that it is in the charged, so you can see the charges. Right, where you have a positive on the phosphorus and a negative on that carbon. Right, so again, resonance structures, same thing. We've got a phosphorus ylide. And you'll notice that we have an aldehyde, right? I said that you're going to have some sort of aldehyde or ketone. Here's my aldehyde. And we're going to have an ylide, which I drew here in blue. As far as the reaction goes, if you're just like, hey, what happens at the end of this? All you're going to do is you're going to replace that carbonyl oxygen with the group that was with all of the carbon pieces on that ylide. So you're just going to kind of cut off that triphenylphosphine, and you're going to cut off the oxygen, and you're going to attach the two pieces together and make a new carbon-carbon bond. So what do I mean by that? So I'm just going to replace, right, this oxygen right here on the carbonyl. That's going to be gone. I'm going to look at my ylide. Right here was the triphenylphosphine piece. That's going to be gone. And I'm going to stick those two pieces together. Right? So I have this piece right here with an H, and there's a double bond going off to who knows what. And here I had this piece with a double bond going off to who knows what. And so we just slap those two pieces together. So now I'll have this is my bond part from my aldehyde, but is now going to be double bonded to, and maybe I'll draw this in a different color just to emphasize the difference here. I'll draw it in green. The part from this phosphorus here, let's do this. Let's go way back. Erase that. right? So then this other piece is this, I'll draw it in green right here, right? Double bonded off into nowhere. That double bonded piece now is going to be coming off here, right? So that's carbons 1, 2, and 3. So carbon 1, 2, and 3. 1, 2, and 3, right? This is carbon 1, 2, and 3. And so you're just attaching those two pieces there, right? You cut this bond here, you cut this bond here, and you attach those two pieces together. And this would be your product, right? Or in other words, if I draw it so it's a little more cleaned up, this would be my product, right? You'll notice that this might not look like the most stable isomer of this, right? Because we have the Z alkene. But we'll talk a little bit more later that you tend to get Z alkenes with a lot of these Wittig reactions. If it's not a stabilized ylide, you tend to get a lot of Z. If it's stabilized, you can get a lot of E. And we'll talk more about that later. But again, right, I just replaced the carbonyl oxygen with the carbon groups that were on the ylide, the thing that was not the triphenylphosphine piece. So let's talk more about that. Now, how do we make these ylides, right? I need to learn how to make these reagents first. So we have two different ways, kind of the unstabilized ylides and stabilized ylides. They're both similar in that they're both SN2 reactions and then acid-base reactions, but I just want to make sure that we know the difference between unstabilized ylide and stabilized ylide. An example of an unstabilized ylide would be something like this. So let's say positive and then just negative, right? So just like an ethyl, this would just be like an ethyl ylide, an ethyl Wittig. Oh, sorry, and this should be pH 3. So pH 3. An example of a stabilized ylide would look more like this. So pH 3, positive, negative, but now let's say I put a ketone here, right? And the idea here is that your stabilized ylide is more stable because you're stabilizing the anion, that negative charge, right? In a stabilized ylide, I can have these electrons drop down and kick up and provide for me a resonance structure, right? I can see that they're delocalized, pH 3, P+, and now there's a double bond here and you have an O-, right? So we would say that that is what we mean by stabilized. Stabilized means that you can delocalize that negative charge. I'll put it out here. So I'll put a delocalized anion versus up here, it's a localized anion. That's the big difference. So how do we make these? If I wanted to make this one up here with just this ethyl piece, the idea is you would just take an ethyl bromide and you would add triphenylphosphine, pH 3P, and all this is going to do is just does an SN2 reaction. Boom, kicks that out. And so you do a good old SN2 reaction. Now you've got your triphenylphosphine that is now attached, but now it's a positive charge. And then you've got your Br-, right? Br-. This is often how you'll buy some of these ylide precursors. They don't always come in ylide form. Sometimes they're not very stable. But so you're always going to have the same first step where you do that SN2 thing, right? This is just a good old SN2. And then the second step is you need to deprotonate. So to get to the final product, you need to do an acid-base reaction. And for this case, for all the unstabilized ylide versions, your second step, you need to have a pretty strong base to make that anion, right? That anion is more stable than just a regular anion because it's next to the phosphorus and it's being delocalized into the phosphorus, but you still need a pretty strong one. So you'll add some sort of very, very strong base, right? So common examples would be like butyllithium, maybe LDA, stuff like that, NaH, any of these, right? These are very strong bases. So any of these very strong bases will work great to help to deprotonate that hydrogen so you can get that anion, right? So bases. And if I take a look at this, let's just say I use LDA since that's a base we're really familiar with. I'll draw the two H's here. And let's say I am going to use LDA. So here's my nitrogen with its isopropyls. Right, and you got your lithium counterion. Then the idea is that it's just your LDA is going to deprotonate that hydrogen to then give you your Ylide that we were talking about here, right? So then you've got your Ylide. And then you take that Ylide, add it to a carbonyl. Now it's basically the same sort of thing down here for the stabilized ones. The only real difference is that you don't have to go with a crazy strong base. You can use normal bases, hydroxide, stuff like that. It's not very hard to deprotonate them because the anions are so stable. So if I wanted to make this Ylide, I would start with the carbonyl compound. Double bond O with a bromine on it. I would do the same step 1, which is to add the triphenylphosphine. So again, you're just doing that SN2 to kick out that group, which would give us our PH3, P with a plus. And in order to turn it into the Ylide that I wanted, again, step 2, you just need to do some sort of acid-base reaction, but you can just add a normal strong base. So I used hydroxide a lot personally, actually, when I was doing these. So even something like NaOH. It doesn't have to be a crazy strong one like a negative nitrogen or a negative carbon or a negative H like up above. It can just be something like hydroxide. Works totally fine. But it is the same 2 steps, right? And I'll label that on this too. Right, this is just SN2. This is just acid base. Same exact idea. Oh, let me draw out that second step for you because I know someone's going to want to see it. Right, so if I had a hydroxide, then we just have this attack that, and then you get your Ylide. And again, these stabilized Ylides, because they're stabilized, you can actually buy a lot of these as the Ylide forms, so you don't even need to do sort of an acid-base, that last acid-base step. So that's how we make the Ylides. Let's talk more about how these Ylides then do this reduction, how they change this carbonyl into an alkene. So let's take a look at the mechanism here, right? This is, I think I put this example up before. We already know that if I do this reaction, I'm going to get something like this. Right, this is the alkene I'm going to get. I'm going to get that one. Now, I didn't mention, well, I did mention it earlier, right? Just keep in mind that if I looked at this, if I was like, well, what product should I get here? If I look at this, I see that this is an unstabilized Ylide because there's no extra withdrawing group on that molecule that's pulling electrons out, that's stabilizing it through delocalization. So when I draw my product, I know that I'm going to be going for the Z alkene. They're going to be on the same side, right? It's going to be the less stable looking alkene, which feels awkward. I posted on our site a great post that I saw a while ago explaining exactly why it does this, because you'd think that there'd be a lot of great reasons as far as the product goes thermodynamically, why you should end up with the trans or the E alkene instead. But there's a transition state in there using a little bit of MO theory that explains why we think at least that it does this. So if you're interested in that, read it. I'm not going to ask you about it, but I do expect for you to know that it forms primarily the Z as the major product. So for the Z for the unstabilized Ylides, E for the stabilized. So let me draw out this mechanism. We'll put my lone pairs on my oxygens. I'm going to remind myself here, right, that this Ylide can also be drawn out like this. And so it's kind of got that positive there and a negative there, right? So that's kind of how the charges line up. If I look over at my starting material, right, my aldehyde here, I know that aldehyde is partially negative and this carbon is partially positive. So what I'm going to do here is I'm just going to line these up and get my positives and negatives to kind of line up here, right? So I'm going to call this, got my H, got my double bond O. I'm just going to call this propyl if that's okay, right? So this just propyl, just to save myself some room. And I'm going to line this up, right? We said that the oxygen was partially negative, carbon's partially positive. So I'm going to line up my Ylides so that the negative carbon is down here, right? And then it has this like isopropyl thing, so I've got a negative carbon. And then I've got my phosphorus, and it's 3 phenyl groups. So now I've got my positives and negatives kind of all lined up to one another. And what happens is it appears that this mechanism, especially for the unstabilized Ylides, tends to be more of a 2+2 type of mechanism where the electrons from this anion are going to attack that carbon-carbonyl, right, which forces those pi electrons to break, right? Normally we'd say they would just kick up onto the O. But I have this positive phosphorus here, so it also is going to pick up those electrons. You're not going to form a negative O by itself. It's going to basically immediately make an OP bond. And phosphorus is very oxyphilic, so it makes nice, strong bonds with oxygen, which means we're going to have a transition state. Or sorry, not a transition state. We're going to have an intermediate. Maybe I will draw the transition state down here for you all, just so you can kind of see it. The transition state here would look like this. All right, where I have an isopropyl, I have the phosphorus with the 3 phenols. And as far as the electrons that are moving around go, right, we're forming a bond here, we're breaking this double bond, and we're forming this bond between the phosphorus and the oxygen, right? That would be the transition state that leads to this intermediate, this 4-membered ring here. Right, there's an H there, there's also that isopropyl, there's an H here, there's also a propyl. And so this would be your intermediate, not very stable, right? 4-member rings aren't very stable. And so you move 2 more electrons, kind of like another 2+2 type reaction, so that the oxygen and phosphorus are now double bonded to each other, and your 2 carbons are double bonded to each other. All right, sorry, I was asked the intermediate to go from there to there. And so now you end up with oxygen double bonded to a phosphorus with 3 phenols on it. And now you end up with your carbons double bonded to one another, right? Which is exactly what we're saying. So now you have a carbon with your propyl and your H. Now it's double bonded to the carbon with the H and the isopropyl, which, like we were saying, right, is basically that just drawn out. And so you're always gonna make this triphenylphosphine oxide waste, right? This is just waste. It's just side product. And, you know, I liked to do a lot of green chemistry. I tried to green up pretty much everything that I did because I don't like throwing it into the environment. I want to keep it safer for myself and my lab mates. And so doing these Wittigs, and like I said, I did so many. I always felt bad because it's so wasteful, right? This is not very green. Producing all this waste is not very green. So that kind of killed me. But I was trying to do research, so I just did it. So I'll put not very green here, right? Because you have a huge amount of waste. If you look at the number of carbons that are in that triphenylphosphine oxide, remember those phosphines are all, or sorry, the phenols are all aromatic rings, right? 6 carbon aromatic rings, they're all benzene rings. It's a lot more waste going into your side product. Sorry, there's a lot more mass going into your side product than your actual product. And so the atom economy for these reactions is pretty terrible. Because again, you don't use a lot of the reagent actually in your product. But here's the mechanism, right? It's really just kind of 2 steps, right? The 2 things come together and then the 2 things break apart, right? So it's kind of like you got step 1 and step 2. That's really it. Form a 4-membered ring, break the 4-membered ring. So let's look at some examples. So here I have a mix of stabilized and unstabilized Ylides. Most of these I'm giving you a carbonyl and then an Ylide in some form. The last one I'm showing you how to take something, turn it into, oh, I forgot a step on this. Well, that's okay, I'll fix it for you. But how to take something and turn it into an Ylide and actually do the reaction. So let's take a look at this first one up here up top. If I look at this, got an aldehyde, check, I know that works. This is an unstabilized, right? Unstabilized Ylide because I don't see a place where that negative charge could be more delocalized. This is also an unstabilized one since I'm here. This is also an unstabilized one. All right, so number 3 is also unstabilized. Number 4, though, is stabilized. So that's probably going to give me the E, right? And all the rest of these are going to give me Z's. And again, I'm just going to go over and see, okay, well, I'm going to get rid of the oxygen on my aldehyde. Goodbye. I'm going to get rid of the triphenyl piece on this one. Goodbye. And then I'm just going to draw the 2 pieces stuck together. So this is that same butanol. And now it's going to actually, let me draw this over here a little bit more. I need some space. I'm going to draw this. So 1, 2, 3, double bonded now. And then I just attach, let's see, 1 carbon over and then oxygen, oxygen, and this like 5-membered ring thing, right? So that would be my main product. Plus, always there's going to be that triphenyl phosphine oxide that's just waste. Same thing for the second one. Get rid of the O, get rid of the triphenyl phosphine piece. And so I'm just adding that, right? So in this case, oh, I have too many H's here. Sorry. This should actually be no H. There should not be an H there. That should just be 1 H, not 2 H's. Otherwise, you can't fit an anion there. So you might see them written out like that, where they're just in a condensed line and a condensed structural formula. But the big key for you is, you know it's going to be Wittig if you see a triphenyl phosphine piece attached to a carbon. That should just scream Wittig to you. And so for this one, here's my technical issues. Here is my original structure. I know there's going to be a double bond right here now. And since I'm probably going to go for the one that's less stable, the phenyl ring is bigger than the ethyl ring. So I'm going to put my 2 carbon piece right there. All right, because again, if you're keeping count of carbons, that's carbon, I'll call that carbon 1 and 2. That's carbon 1 and 2. Now I've got another one with just acetone. No stereochemistry for that one, so that should be pretty straightforward. All right, again, goodbye O, goodbye triphenyl phosphine piece. Looks like I need to add 1, 2, 3 carbons to this one. So that's exactly what I'll do. Double bond, 1, 2, 3. 3 carbons. So I've made that alkene. And again, you'll notice that these are reductions because you're replacing 2 bonds with something more electronegative to 2 bonds to something that is as electronegative as carbon. Now this one, where I finally had a stabilized one, so I'm not going to get the Z's like I had before. I'm going to go for an E. So for this one, I've got my double bond aldehyde. Now that's a double bond, but I'm going to keep on going. And in this case, it's an isopropyl, but I'm going to have that as my main product, right? And again, notice that I'm going with the E here, right? This is now E. It's opposite, because I'm dealing with a stabilized ylide, not an unstabilized ylide. So you just want to keep that in mind. They tend to form different products. Now for this last one, I forgot a step. Let me add, I'll do step 1A should be the Br2, and I'll do step 1B should be your triphenyl phosphine. Triphenyl phosphine. Forgot a step when I made this. So first step with the bromine, right? That's just a radical halogenation. You use Ylide or something like that, Br2. But that's just going to put a bromine here. It's the most stable spot for radicals near the carbonyl. Then step 2, right? Step 2 is going to turn this into add the phosphine, right? Do that SN2 reaction we were talking about. So then I'd have that. Step 2, the sodium hydroxide stuff is going to make it the ylide. And then the third step, I've got benzaldehyde that I'm adding it to. Now, so I've got my benzaldehyde that I'm adding to this, which is this sucker. So I just need to react that with that. It looks like this ylide is stabilized since it's next to a carbonyl, right? I'm going to have those electrons be delocalized. And so I can just draw my product, which would look something like this. So that's what the Wittig reaction can do. Great, powerful tool for making new carbon-carbon bonds. specifically carbon-carbon double bonds. Introduces an alkene. We know tons of reactions we can do with alkenes. It's a really, really powerful tool. So you are going to see it. And again, it's one of my favorites. So be prepared. So do some practice. Happy studying and good luck.